Okay, here we're going to solve one of the classic optimization problems in calculus. All right, what's going on is we've got a river here, and a farmer wants to create a pasture. Now, he only has to fence in three of the sides, since one of the sides is bounded by the river. And the question is, what's the dimensions that should the farmer create on each side of the pasture so that you'll get the most area? Now, here's the constraint though. You usually only have so much fencing, which is very realistic. So I just kind of made up an example here where we have the constraint of 500 feet of fencing. So what should be the width and the depth of this pasture that he's creating? What would those dimensions be? So we start off by looking for what's called the objective function, and all these optimization problems, the objective function is what you're trying to maximize or minimize. So you look at the question, oftentimes it's written as a word problem, and I see maximum what? Maximum area. So the first thing I want to do is find the area of this pasture here. I know the constraint sounds more like perimeter. We'll get to that in a minute. But what's allowed to vary in this problem is the width and the depth of the dimensions. So we'll put variable names here. We'll call this x, and we'll call this side y. Or vice versa, it doesn't matter which. You could call it y and x, that's okay. And if this is x, then this would have to be x just because those sides match. It's a rectangular pasture. And the area of the pasture would be length times width, x times y. Now herein lies the problem for all optimization problems. If you've seen one of my other videos on another optimization problem, you'll notice the same issue occurring again and again, and the examples you've done in class and the ones in the textbook. What you're trying to maximize, which is this guy, which is area, ideally, if you were going to find a maximum, because usually this section follows the sections taught on relative extrema or local maxes and mins, you would draw this function, or you wouldn't even have to draw it really. But the point is you would find a critical point where the derivative equals 0 and solve it, and whatever x value makes the derivative be 0 is likely to be your max or your min. Right? It would be this place right here. But now here's the underlying problem. This assumes that a is only in terms of a single variable, right? Because this is two-dimensional. A is the dependent variable, and it depends on t, x, y, whatever. So whatever's in your particular problem. But here, most of these objective functions and these optimization problems aren't in terms of just one variable, but two variables. Now that's a problem. So what do? Well, we actually use this constraint that's provided to knock the number of independent variables from 2 down to 1 because they should be interrelated. If we only have 500 feet of fencing, we can write that as an equation. So let's do that. 500 would be equal to x plus y plus x. That's all the fencing. This length plus this length plus this length would have to add up to 500. All right, now what that's going to let us do is solve for one variable in terms of the other guy. So this will be 500 minus x makes minus 2x. And the reason that's so incredibly helpful is this objective function, this area function that was x times y. Well, now I have an equation for y that's written in terms of x. So I can write the area not just as a function of x and y, but of simply x, and that's tremendously helpful. So instead of x times y, since y and 500 minus 2x were equivalent, they were worth the same amount, and I'm going to substitute y for 500 minus 2x. And that's the key step, because from there, now that we have the area written just as a function of x, I can proceed as normal in finding relative maxes and all that good stuff. So first things first, let me rewrite it. 500x minus 2x squared. Then I'll take a derivative to find the critical point. 500 minus 4x. So this would happen, or we'll set this equal to 0. And that would be equal to 0 when x is 500 over 4, or 250 over 2, or 125 feet. All right. Now that's just the x coordinate and the x coordinate only for the dimension of maximum area. We also have to go back and find the y. So somewhere in all of our previous work, there should be some relationship that relates x and y. It's not the objective function. It comes in the constraint. You see right here where y is equal to 2x. Well, if you know x, well then obviously you could find y. So do a little math. 125 times 2 is 250, and 500 minus 250 is 250 feet. So it turns out these are the dimensions that'll maximize this farmer's area in his pasture while using up 500 feet of fencing. You'll have 125 for the depth and 250 for the length. Now, one thing I want to caution you about before we end this video is, and I was guilty of this as a student as well, you start trying to justify this answer backwards using just some simple logic. Well, if you didn't use this side, then the optimal dimensions would probably make this two squares, and you just start going off on these little tangents, just trying to justify your answer in an, here's the key word, informal way. That will really get you in trouble. It'll really burn you. You need to keep this consistent philosophy of writing an objective function, using the constraint to eliminate one of your variables, taking derivatives and using the first derivative test or second derivative test to really guarantee that these are maxes and mins, etc. Really try to avoid that fuzzy math, the generalized, type of arguments as to why something would be right. Because, 9 times out of 10, the logic may have some truthfulness to it, but it's not what we call rigorous. And mathematics is really heavily grounded in rigorous mathematics, as having indisputable steps written out from top to bottom. So that's just my 2 cents there. If you're taking a test, really make sure you show your work well and really explain to the teacher why you're getting these answers and not stay away from the fuzzy logic. So I hope that helped. This is one of the classic optimization problems. There are plenty of others, and we'll do some of those in these upcoming videos.